Welcome, everyone, to our ARSET training series, Introduction to NASA Earth Observations and Tools for Wildfire Monitoring and Management. Today is part 1 of our training series, Introduction to Satellite-Based Active Fire Detection Using FIRMS. My name is Melanie Follette-Cook. I am a researcher at NASA Goddard Space Flight Center outside Washington, D.C., and I'm the project scientist of the ARSET program. So first, before we begin today's training, I'll say a few quick words about ARSET. The NASA Applied Remote Sensing Training, or ARSET program, provides cost-free training on the use of remote sensing observations, analysis methods, and tools. We provide training in several thematic areas, including agriculture, climate and resilience, disasters, ecological conservation, health and air quality, water resources, and wildland fires. ARSET provides training both online or in person. Our online trainings are delivered in 2 formats, live and instructor-led like today's training, or asynchronous and self-paced. Like NASA's free and accessible data, all of our trainings are offered at no cost. We try to offer trainings in more than one language whenever we can, and we only use no-cost and open-source software and data. We offer our trainings at a range of levels, so you can find a training series that fits your level of experience and need. Please visit us at our website to learn more. We'll start today by giving an overview of this training series, Introduction to NASA Earth Observations and Tools for Wildfire Monitoring and Management. Every day, satellite sensors are able to detect thousands of fires from space. When these satellite observations are available in near real time, they can provide timely, comprehensive, and actionable information for wildfire applications. Near real-time observations enable rapid detection and monitoring of fires, including their extent, intensity, and spread, which is invaluable for strategic planning and resource allocation. Satellite observations can also support the assessment of fire impacts on ecosystems, infrastructure, and air quality, and aid in post-fire recovery efforts by providing accurate burn scar mapping and monitoring vegetation regrowth. By the end of this training series, we hope that you'll be able to evaluate different satellite-based active fire detection data sources using FIRMS to build a wildfire narrative, understand the strengths and limitations of each source for different types and sizes of fires, apply FIRMS data and tools to evaluate rapidly growing wildfires using the tools available in FIRMS, apply strategies using FIRMS to identify factors that can impact satellite-based wildfire detection, resulting in a missed wildfire, and make a plan for when data may become available. Use FIRMS to monitor a particular area of interest by accessing active fire data from the archive available. Use web services to create an email alert for your area, or ingest the resulting fire alerts into a GIS platform to enable evaluation. As a prerequisite to this course, we recommended that you take our Fundamentals of Remote Sensing training to familiarize yourself with terminology and concepts you might hear in today's training. Some examples that might be important to today are what's meant by the spatial or temporal resolution of a sensor, or the difference between true color and false color imagery, and how false color imagery is used to enhance surface features like the presence of vegetation or a burn scar. In part 1 today, we'll introduce the Fire Information for Resource Management System, or FIRMS. Parts 2 and 3 will cover how to use FIRMS for wildfire monitoring and evaluation, and how to access data through FIRMS. A certificate of completion will be awarded to participants who attend all live sessions and complete the homework assignment before the given due date. And with that, we'll begin part 1, Introduction to Satellite-Based Active Fire Detection Using the Fire Information for Resource Management System, or FIRMS. I'm very happy to introduce our guest instructors for part 1. Jenny Hewson is the Outreach and Implementation Manager for NASA's Land, Atmosphere, Near Real-Time Capability for Earth Observation, or LANCE. Brad Quayle joins us from the U.S. Forest Service, where he is the program lead for the Disturbance Assessment and Services Program. By the end of today, part 1, we hope that you'll be able to recognize how active fires can be detected by satellite sensors. Use FIRMS to view active fire information and identify the strengths and limitations of polar and geostationary satellite sensors to detect different types and sizes of fires. If you have questions during today's training, you can put them in the Q&A box there within WebEx at any time. At the end of the training, we will try and address as many questions as we can, and we'll post the questions and written answers to the training page, to the firm's training page, within a week after the training. And now I am happy to turn it over to Brad.
All right, well, thank you, Melanie. This slide here provides an outline of the topics we're going to cover in our presentations today. First, I'll be providing a brief introduction to firms and also some information about satellite-based fire detection and also an overview of the data that's included in firms. And then I'll pass it to Jenny, who will be talking about information related to the strengths and limitations of different satellite-based active fire detection products and sensors. So our first section here on the introduction or an overview of firms. Firms is the Fire Information Resource Management System, which is developed by NASA, and it provides timely active fire detection data, imagery, and other relevant data from a variety of satellite sensors for the entire globe. The main objectives of firms are to enable access to spatially and temporally comprehensive satellite imagery, active fire detections, and other relevant data at the lowest possible latency. It also works to facilitate the availability of a big picture of fire activity and allowing users to detect and monitor fires and assess their effects globally. And lastly, we also provide a series of tools and capabilities and interfaces that help support operational agencies with fire planning and response, as well as academia with research initiatives, and also to meet a variety of other needs in the user community. Firms consist of two distinct applications. The first one is called Firms Global. It was developed by the University of Maryland in the early 2000s. Then later on, about in 2012, it was migrated into the NASA Lance framework. And Firms Global is intended to provide access to a large suite of low latency satellite imagery and derived fire science remote sensing products at a global scale. And its sister application is called Firms US Canada. This application was developed in 2021 through a cooperative effort between NASA and the Forest Service that builds upon a long history of close coordination between the two agencies on strategic active fire detection and monitoring activities. This started back in 2000 with the development of the initial Modus Rapid Response System. But Firms US Canada is very similar to Firms Global, but is focused on the US and Canada geographic area. It provides the same data sources that are available in Firms Global, as well as some additional data that are specific and relevant to fire management agencies in the US and Canada. Now we're going to talk a little bit about satellite-based fire detection. Firms provides many imagery and data products for detecting, monitoring, and assessing the effects of fires. Active fire detection data are the most frequently used data products in firms, and these data are provided using multiple satellite sensors. And based on the various technical aspects of these sensors, as well as the orbit configurations of their respective satellite platforms, the timing and frequency of these satellite observations for active fire detection can vary. Active fire detection products are generated using active fire detection algorithms, and they leverage multispectral data spanning from the visible clear through to the infrared wavelengths of the electromagnetic spectrum. And these fire detection algorithms are designed to exploit the response of fire in the mid-infrared and the long-wave infrared wavelengths, typically at 4 microns and 11 microns, respectively. And this chart illustrates how you have a significantly stronger response of fire in the 4 micron band or the mid-wave infrared relative to the long-wave infrared. And it also illustrates how the mid-wave infrared is very sensitive to both flaming and smoldering fires, and that corresponding response by the long-wave infrared band is significantly less. And this contrast between the fire signal in these two bands helps improve the detection capabilities for these algorithms. And these fire detection algorithms also leverage selected visible and near-infrared bands to help identify and mitigate the effects of things like sun glint, which can result in false positives, and also to identify and mask out particular features. Fire detection algorithms for MODIS, BEERS, and various geostationary sensors are based on the legacy approach that was developed back in the early 1980s by Jeff Dozier for the advanced very high resolution radiometer sensor. And this flowchart that's shown on the screen right now provides an overview of the key steps that are covered in the MODIS detection algorithm, which is based on that legacy algorithm approach. And basically what happens here in that first group, with an incoming image, the invalid data is removed. This is where you have missing data pixels and things like that. And then masking processes occur where there's a predetermined land water mask that's applied, so that we're just working with land pixels and all the water is removed. And then some spectral thresholding is applied to remove things like clouds and so forth that could interfere with the performance of the algorithm. And then we slip into what's called the tentative fire pixel detection stage. And that's where some absolute thresholding is applied to the 4-micron band or the mid-infrared band. That's just above basically the nominal surface of the Earth to identify any potential fire pixels. And then these pixels are then subsequently evaluated again with some more conservative thresholds in the 4-micron band to identify those very obvious, unambiguous fires based on that response in that band. And then both the potential pixels and those obvious fire pixels are then evaluated in the context of their adjacent pixels in that neighborhood, and some statistical analysis is performed to evaluate how much differentiation there is between that targeted fire pixel that's being evaluated in its neighbors. And based on that statistical analysis and the differences in the response in the mid-infrared band, as well as the delta or the difference in the response in the mid-infrared and the long-wave infrared, we can have an output and determine whether or not that is indeed a fire detection or not, and what our confidence is in it being a detection. And then subsequent to that, a series of tests are conducted to reject fires that we identified in the previous step that might be a result of sun glint that affects that mid-infrared band. We use the visible bands and near-infrared bands to eliminate those potential sun glint cases, and also the heterogeneity of the landscape around those potential fire pixels and that contextual analysis mentioned before. They can contribute and provide some statistics that could affect the confidence that on whether or not that is a fire or not. So those are areas where you have very discrete ecotones, like between a desert and a non-desert area, or maybe water versus non-watered areas or forest clearings. Some additional analyses can be done there to eliminate those areas, or at least reduce the confidence of those detections. And of course, there's always challenges of the accuracy of the water mask along the oceans or other large bodies of water, and some additional spectral tests can be conducted to identify pixels that are water that are not picked up in the water mask, or mixed water and land pixels, and remove those from consideration. Ultimately, the output is a raster data set like you see on the right here for the entire image, identifying those fires at different levels of confidence, as well as land, clouds, and water that were identified in the process. So what does a fire detection mean on the ground? Basically, it can be representative of multiple conditions that's driven by the characteristics of the fire. A detection could be representative of a fire that's very small, very hot and intense, or it could be representative of a bigger, broader, cooler burning fire, or a combination thereof. Typically, it's the former example that I mentioned where that takes place. There's one or two small fires in a pixel that's much smaller than the resolution of the sensor resolution that's being detected, and in those cases, the entire pixel is identified as a detection. So with MODIS, the entire 1 kilometer pixel is identified as a fire detection, but the actual fire within that pixel is actually much smaller than that fire, or I should say that spatial resolution of the pixel. This example of this image on the right is a Terra MODIS false color composite, and with that false color composite you can see the fire activity in the reddish to orange glowing areas in the northwest and the southeast part of the image, and you can see in the black outlines are the MODIS active fire detection outputs at 1 kilometer resolution. And you can see in those given pixels where some pixels have a significant amount of fire activity within them that are visible in this false color composite. Others have less so, and some you can't even see at all with this false color composite. However, there is enough of a response there in the mid-infrared and long-wave infrared bands that the algorithm can detect the activity there in those smaller fires that are not visible at this resolution of the imagery to the human eye. So the pixel size for fire detection data that are provided in firms varies. It's determined by the spatial resolution of the source sensor system that's being used. And as I mentioned before, we use a lot of different satellite systems that are contributing fire detection data to firms. And that those spatial resolutions of those sensors can range from 30 meters up to 3 kilometers. And the coordinates of those centroids we can easily calculate and extract from the fire detection outputs. And then we can use that information to map in firms in the interactive map interface, as well as to develop a whole host of geospatial products that we distribute from the firm's framework as well. A little more discussion about what detection means on the ground. In addition to the fire characteristics I mentioned on the previous slide, there's a whole host of other factors that can, contributes to the ability to detect fire activity using satellites. One factor relates just to the physical parameters of the satellite and the sensor itself. So like the altitude of the sensor and the scan angle or the view angle that the sensor sees at the time of overpass is an important consideration. For example, polar orbiters, when they make that overpass, they're looking out about 55 degrees either side of the point below them, what we call nadir. And geostationary sensors see or have an even wider framework of view. They are looking outwards up to about 85 degrees. Well, that increase at those pixels that make up the satellite image, we see those increasingly higher view angles out towards the edges of what we call the swath or the frame of view due to that increasing distance and from nadir and the curvature of the Earth, that can create what we call a distorted instantaneous field of view for those pixels, and those pixels get stretched and distorted in both dimensions. And this is a common issue in sensors like MODIS and GOES, Advanced Baseline Imager Sensor, and some others. And so the multispectral responses that we receive for each of those pixels that are distorted can cause errors in what the signal that's received, which can contribute to errors in the output fire detection algorithm products as well. And we'll highlight these issues later on in the presentation and throughout the training session. The timing of satellite overpass or observation is another thing to consider. Sometimes, with the polar orbiters, I should say, we don't have fire activity maybe going on when the satellite goes over. And so it's just a matter of timing of the fire when it's burning and when the satellite is able to detect it at the time of observation. Geostationary sensors, it's a different story because they have a persistent capability or persistent observation capability, and they're constantly staring and taking observations at a very high temporal frequency. There's various other environmental factors that also affect the detection capability of a fire. That includes the fire size and intensity, as mentioned in the previous slides, but also very thick cloud cover and smoke cover can also prohibit the ability of the sensor to see those infrared signals and detect the fire. And also fires burning under thick tree canopy cover cannot be detected as well. And of course, terrain, if you have a fire that's in a very steep canyon, and depending on the view angle properties, it may not have the line of sight to detect that fire activity. And of course, the heterogeneity of the local land cover, where the fire detection algorithms making that assessment of determining if it's a detection or not can also contribute to the at least the accuracy and reliability of those fire detection outputs. So what sizes and types of fires can be detected by satellite? Well, polar orbiting sensors are used quite frequently in fire detection and monitoring, and that's because they have very good spatial resolution compared to geostationary sensors. This slide here shows the what we call the lower size limits of fires that can be detected by sensors that are commonly used in firms, MODIS and BEERS and Landsat. And you see the varying spatial resolutions as well for each one of those sensors, which is also portrayed graphically on the right, so you have an appreciation of their footprint. Essentially, the much smaller fires can be detected, as you can see, the much smaller fires can be detected under nighttime conditions because there's more discrimination between the radiance from those fires compared to their background conditions in the night than during the day. And also, you need to be very careful still in using algorithms or active fire detection data, because algorithms are not perfect, and also the data that goes into them are not perfect, and they may be prone to error that we can't account for. So again, always use these data cautiously and pay attention to the confidence ratings of the data when you're using it and for applications. So let's get back to the use of active fire detection data and the sources that are available within firms. Firms uses multiple satellites and sensors to detect and monitor fire activity and provide other various fire science remote sensing products. And currently we use 15 satellite missions in firms that are managed by 5 space agencies throughout the world, and collectively this provides access to 16 satellite sensors that we provide operational data from and integrate into firms on a daily basis. Firms utilizes relevant science products from a variety of satellite missions throughout the world, and this table summarizes those products that we currently provide in firms. We provide active fire detection data from 12 satellite sensors right now, and we're actively working with science teams from NASA and also the European Space Agency and EUMETSAT to provide operational active fire detection data from Sentinel-3 SLSTR in the near future. We also provide true and false color imagery from all these satellite sensors, with the exception of a few geostationary sensors. We have yet to integrate false color composite imagery, but we're actively working on that. And of course, we also use the day-night band imagery products that are available from BEERS. And we also integrate the burned area product that's available from MODIS, and we're actively working with PIs at NASA and the University of Maryland to develop and implement a near real-time BEERS burned area product in the next year or so. And we also are integrating or have integrated the harmonized Landsat Sentinel imagery data, and recently that NASA effort has started to make available a whole suite of vegetation indices, and we're actively working to integrate various fire-related indices from that product suite, including NBR and NDVI and so forth, into firms. And aerosol indices from the various satellite missions we also incorporate, so folks can track the migration and movement of smoke from various fires. And snow cover is a product that we are now providing from BEERS. And the purpose of that product is to monitor the recession or change of the snow line in the spring as the snow moves back. Fire managers can then start paying attention to those areas more closely and watching the fire danger forecasts and whatnot, and the increasing fire danger. Firms doesn't directly produce all the fire detection data, imagery, and other types of data that makes available. These data are all made available via partnerships firms has established with agencies and programs and institutions, including the global near real-time data feed that's provided by NASA Lands. And recently, firms has put a lot of increased emphasis on further lowering the latency of our products, particularly active fire detection, wherever that is possible. Before the last year or so, the system was entirely fed by the NASA LANC system, which has a latency of 1 to 3 hours globally. But we've actively been incorporating the use of direct readout data, at least in the United States and Canada. We have several direct readout ground stations we have access to through our partners at the University of Wisconsin, and they're using NASA algorithms to provide us active fire detection data that we can provide for that geographic area. We've also been working closely with our partners at the University of Maryland and USGS Aeros Data Center to provide 30-meter Landsat active fire detection data. And we use the ground station capabilities in Sioux Falls, South Dakota, and the Landsat data that's collected there to provide those data in real time and deliver it to users in the US and Canada and Mexico area. And lastly, we've actively been working with all the space agencies that manage geostationary satellite assets throughout the world and acquiring their data and processing it to provide active fire detection data using the latest science-based algorithms that are, or science-sanctioned algorithms that are available, and providing those data in real time. And this is just intended to be a highlight of these activities, and we'll be discussing these activities in more detail throughout this training session. So the next part of the session is we're going to do a little demo and talk about how you can access active fire information using firms. So when you go to global firms at this address here, this is what you see when you start. This is what we call our landing page, or the gateway page to all the functions and tools and capabilities of firms. There's the fire map, which we'll be spending some time on here in a few minutes, and you can go and use this interactive map viewer through that gateway. Active fire detection data, you can download data as comma separated value files, as reshaped files, and the KMLs and whatnot. We have a whole suite of formats that the active fire detection data are available in and can be consumed by a variety of software applications. If you're interested in setting up an alert for a geographic area of interest, you can visit this portal and define that area, and you'll receive notifications when an active fire detection has occurred in that area. You can also order and download historical active fire detection data from MODIS and VIIRS and Landsat data that are archived by the firm's system. And of course, you can access web mapping services, both WMS and WFS format, for consuming in desktop GIS applications or web applications that you're building yourself. The firm's US-Canada has the same look and feel for that gateway, and I'll highlight again some differences between firms US-Canada and firms global as we go through this demonstration here. But if we jump into the fire map, this is what the interface looks like for the fire map, and most users, when they work with firms data, are working with the fire map. And it's the typical type of web mapping interface, but it's very, very rich in data sources and tools and capabilities. When you, if you visit the little hamburger icon here on the left, you can easily jump to any of those gateways to other sources of data in different formats, as well as you can create image subsets. We have blogs to post information about new data sources and capabilities in firms. We also provide tutorials, and we also have a very robust FAQ page, and then other related support resources that might be of interest. So all those things I just mentioned are provided in addition to the standard products and services that are available. So that stays up there docked on your side of your map, if you like. We have you zoom in, zoom out buttons, location tools, the scale bar. We have a toolbar down here that allows you to do various functions that we'll highlight here in a second. I'll just turn on the timeline here. This is a time slider bar that allows you to set the date if you prefer here. And then we have the various buttons up here in the upper right. The most important being the announcement button, and you can go there to see if there's any new announcements that the firm's team has put out or NASA has put out that would affect data or information that's provided on firms, and we'll highlight that here in a second. And of course, feedback. If you're interested in providing feedback to the firm's team about the interface, or if you have a question about the data, feel free to send us an email and the firm's team will respond to you. As I mentioned before, the firm's interface is very rich and has a lot of layers and functionality. So to make it scalable to best meet user needs, when you first jump into the firms, it'll be in what we call basic mode, which provides just the polar orbiting active fire detection data, as well as a limited number of image resources, image layers, I should say, and also some various static backgrounds and some overlay layers here as well. But if you click on the little hamburger icon here, you can change into various modes that we have predefined to meet particular user needs. If you're interested in looking at burned area products or looking at products relevant to tracking smoke and aerosols, you can jump into those respective modes. And you can jump into what we call advanced mode. And we also have what we call an experimental mode, where we're putting products that maybe NASA science teams have released in a kind of a beta form, if you will. They're not quite ready yet for operations, but we'd like to make them available to the user community to take a look at and maybe provide some feedback on, and we can also assess and see how they perform before we fully integrate them into the interface. So if we jump into the advanced mode, that's the most robust mode. You have the most layers to choose from and functionality. And so when you first jump in, you have the capability to set what I call your reach back threshold. And by default, you can see all the detections for what we call today. And that's everything that's as of midnight UTC time to the present time. If you set it to the 24-hour window, you're seeing everything basically for the last roughly day to 2 days. And if you want to see what those things mean, or if you need information on anything in the firm's interface, click on the little I button or icons here, and you can see, as I described here, what does it mean, or how far is your reach back when you have it set to today, or 24 hours back, or 3 days back, and you can see those time thresholds that are being applied. And we have some various tools here to, we're displaying all the data for the entire day. You can also make sub-selections or filtered fire detection data to, particular hourly periods within a day, if you like. And we'll be talking about that later in the training. And of course, you can also set the calendar date for that you're interested in. By default, firms will show up for the current day that we're on. And this is another reach back capability. You can go back 31 days in displaying fire detection data on this map in firms. And of course, you have all the polar orbiting data. And if you open up the layer here for geostationary, these are all the sources of geostationary active fire detection data that are available. And again, the info button is your friend. If you click on these buttons for the layers, it'll take you to a pop-up page that'll tell you all about that particular data product, where it's coming from, attributes that are associated with it, and a description of those attributes. And as you can see, we also have our data divided up into groups. And if you click on those little info buttons for those groups, it gives you a brief description of what's in that particular group. So there's a description of what's in the polar orbiting group. Here's a description of what's in the geostationary active fire detection data group, and so forth. Down here, we also have orbit tracks for polar orbiting sensors. So you can get the ascending and descending orbit tracks for the current calendar day you have set for all these various instruments that we use and provide data from in firms. You also have access to the MODIS burned area product, which is that 500-meter spatial resolution product that's compiled on a monthly time step, and you have full reach back for the entire MODIS record for that product for display. And as noted here, this is not a real-time product. due to the way that that product is generated, there's a bit of a lag there, but it's typically available in firms about 3 months after the current date. Current or gridded fire hotspots, we'll talk about that in a minute, but it allows you basically to summarize and view fire detections at a coarser scale and infer information from it. Aerosol indices, we currently provide aerosol indices from SNPP OMPS, or the ozone mapping ozone mapper and profiler suite, and we're working on integrating OMPS data from NOAA 20 and 21 as soon as it's available and produced in near real time. And we also have a whole series of contextual data layers for overlays that may help you out in using the data. And as I mentioned in the previous slides, we do provide access to the harmonized Landsat Sentinel-2 imagery for the entire globe, both in a true color and false color format. Drop the data here real quickly for Landsat. If I set the date back a couple days, because these data are available on about a 2 to 4 day delay. They're not available in real time, so you can see this is all the Landsat 8 and Landsat 9 acquisitions on this particular date, and here are all the Sentinel-2 acquisitions. The missing pixels here are where the data is masked out because it's too cloudy and doesn't meet that cloud threshold. And of course, we have all the satellite imagery from VIIRS, MODIS, and true color composites, as well as false color composites from all of those sensors. And we also have the day-night band products from VIIRS, SMPP, and NOAA 20. And we'll be working on getting NOAA 21 VIIRS nighttime products integrated as well. And of course, we also have GOES imagery for right now. So turn this off for a moment, and I'm going to jump here to the 22nd, or I should say the 27th of March. As you can see here, I have a 1 day reach back. I'm looking at the current day's worth of fire detections for all the polar orbiting sensors. And I'm going to turn some of these groups off just so the list is not so long. And there's a lot of detections. By default, the fire detections from all the polar orbiting sensors show up in different colors of red, and that can be kind of overwhelming to look at that. But you can use different classification schemes we have loaded up. This is what we call our time since detection, or TSD classification, and what it's showing me in intervals of hours, how current those detections are to now based on when they were observed. So the bright red ones are in the last hour, and the lighter red ones are in the last 1 to 3 hours, and then the orange are in the 3 to 6 hour range, on up to yellow, which is just outside of 24 hours. We won't have any in that last category since we're just looking at the last day, but if I wanted to do a little bit more of a reach back, say to a week, then I'd definitely have a lot more of those fire detection pixels beyond the last 24 hours now displaying. I can also change that to days, time since detection in days. So instead of hourly intervals, we're looking at daily intervals here at that data. So let's take a look at the fire detections in the last couple of days here. And maybe I wanted to, instead of looking at all these detections that are going on, maybe I would like to look at that data in another way. And so going back to our gridded fire hotspots data, I can generate a gridded summary of the active fire detection counts on a 0.25 by 0.25 degree grid. And this is done automatically. So give it a second here and it calculates it. And I can go back up here and turn off those detections. And so basically I have a heat map that's telling me between 1, which is on the yellow end of the range, up to 100 plus on the red side of the range, of how many detections are inside of each one of those quarter degree grids. I can also turn on the labels. you can't, this is computed dynamically, so I can't click on it and get the attribute, but I can at least display those pixel counts as a label, and I can see how many pixels there are, or active fire detection pixels are in that grid. Anyway, I can do that for any of those polar orbiting satellite sources. So let's take a trip back in time to show you how you can have full reach back in firms for all of the satellite missions. So let's jump back just to the summer fire season last year, July 27th, and see what's going on here. Turn on those detections again, and do something here in the last time since detection for the past 24 hours here over this 2-day reach here. So this is everything that's going on in about the last 48 hours as of July 27th, 2004. You can see all the burning that's going on below the equator in Africa, as well as over here in South America, forest clearing in the Amazon, as well as agricultural burning over here, gas flares. You can see a lot of that here and here in the Middle East, and also up here in Western Russia. A lot of these are gas flares, but you can also see the wildfires here in Siberia, as well as in the northwestern United States and northwestern Canada that are going on. So we can take a little bit of a visit here. Take a look at the fire activity here in Northern California. Again, we're looking at everything here. Just to kind of give you an idea of what I was talking about before, you're looking at the various pixel resolutions of the data from the various sensors. We render all those points accordingly. So if I just want to look at the Landsat detections, these are 30-meter cells, and of course 375-meter cells with the Beers data, and 1-kilometer cells from MODIS. So we render those data relative to their nominal spatial resolution. I can take a close look at these detection data relative to the imagery. So I'm looking at NOAA 20 Beers, and if I take a look at the false color composite imagery for NOAA 20, they've got a lot of smoke here, but the shortwave infrared bands in this composite help cut through that smoke. By comparison, if you look at the true color composite, which is just a visible band, you can hardly see anything at all. So if we look at those data there, I can I can then take a look at that, and I can see where those active fires there are. I'm just kind of flickering it there. If I change it to a custom rendering here in firms, I can split it open, and I can say I only want to look at the daytime pass, which would of the active fire detection, which would correlate with this image. I can also adjust the opacity of those detections, so I could swipe it, if you will, to see what's going on, and I can see the active fire front here in this imagery and those detections that were detected at the time of that overpass. And I can do that with all the other sources of detection data as well. So here's NOAA 20 Beer, NOAA 21 Beers, and then I turn on NOAA, I should say SMPP Beers, but nothing comes on. It's empty. Well, why is that? Why am I not getting any data? Well, this is where you could use that announcement information to help you out. If you go down to announcements and the technical issues and outages, you'll be sent to a page here that lists when particular data outages occurred, when they started, and when they were resolved. So if I do a show all, and I was looking again at July 27th of last calendar year, and on the 24th, there were some technical issues that started with SMPP that affected the data processing, and so they halted the data processing. That was later resolved, and production was renewed back on the 30th of July, about a week later. So between the 24th and the 30th, there was just no SMPP data available, so which is why you don't see any SMPP VIIRS satellite detection data, nor do you see any SMPP imagery. So just a little pointer there on how you can use that information to help you sort that that information out. And just one other thing to highlight, the Landsat data, you don't have the same temporal resolution with Landsat that you do with MODIS and VIIRS. Between Landsat 8 and Landsat 9, we're getting a look at any point on the Earth about once every 8 days. At higher latitudes, we get some overlap between the swaths, and you'd have a higher observation frequency than in the mid-latitudes. But again, at the mid-latitudes, you're only going to see it once every 8 days. But when it's available, it's a very highly high spatial resolution resource for looking at fire detects. And if I look at the HLS Landsat imagery that's available on that acquisition from the 27th, takes a second to draw in there because it's higher resolution data. And doing what I did before, I can play some games with the opacity here. I can see that active fire front at a higher spatial resolution of 30 meters and those 30-meter fire detections. So let's draw everything up again, and I'm going to turn off my imagery. So the next thing I wanted to visit with you on, or at least demonstrate, is what if I wanted to find out how far away I am from a fire? Well, there's we have these fires that are going on in Northern California and up here in Oregon, and I can use my location tool, and I can put in this location. Think of it as like a digital gazetteer. I can put in Salt Lake City, which is where I'm located at, and I got my location here. I can save this location for future use, and you can see it here now. It's saved. I can just toggle it and bring it up at any time. So I have this location here established, and let's say I wanted to get a rough idea of how far this fire is away from me over there in California. I can use the measuring tools, and you'll get a little tool that pops up here by default. It's going to measure area, so you have to set it to distance. I can set my units to kilometers or miles, and I can measure from Salt Lake City to that fire and see that's, I'm about 840 kilometers from that fire. And if I was interested in seeing how far I'm from those fires up in Northern Oregon, I'm about 760 kilometers away from those fires. So you can use this information and locational tool to identify the location of anywhere on Earth that's available in that gazetteer, and plot those locations and save them, and use them at your will within the firm's interface. The next thing I'd like to highlight is using those contextual layers that I mentioned. We have a whole list of various overlays that you can utilize. By default, a more generalized border and roads layer is available, but if you wanted a more detailed layer, you can draw those up. I'll zoom in here, and where I'm from here in the Salt Lake area, you can see as you zoom in to larger scale, you get more detail, and so that layer is available. You can also plot the latitude and longitude grid for reference purposes. There's our snow cover layer. I'll zoom out a little bit so you can kind of see what the extent of that is at this time. And then we have a built up, so you can see where all the urbanized or populated places are, which is good. And this is a global product, which is good to have. And if you want to know if fires are threatening any built up areas. And of course, we also have protected areas, national parks, and other types of regions of interest that are protected by the government or other organizations, and understanding the threat of fire in those particular areas. And orbit tracks. I want to highlight that for a moment. If I was interested in knowing when NOAA 21 VIIRS is going to be overpassing the western United States on July 27th, 2024. I can see here's the orbit track there going over the western United States, and here's the orbit before. When I went over the eastern United States, approximately 98 minutes before this western orbit pass. And you can see these time intervals that are marked. These times are in UTC. And if I draw up the imagery, the NOAA 20 imagery, again, this is the center line of that orbit. And the swaths are so wide with veers that they overlap with each other by about 10%. So there's no gap there like you see with MODIS data. So these orbit tracks help you in determining the time of overpass when you're looking at imagery, when you're looking at fire detection data. If I click on the fire detection data, I get all the attributes about that fire detection data, including its latitude and longitude coordinate, its brightness, temperature in the thermal bands, and its what we call here, these are the instantaneous field of view dimensions at that view angle, and also the source of the satellite and the instrument, its confidence level, and the version of the data, and so on and so forth. And again, you can use this information here to determine that time that that fire was detected as well, in addition to the orbit tracks. So the next thing I wanted to show you is how do you share a map in firms. You can do that a couple of ways. You can capture the map you have on the screen. Like if I built this map and I really like it and I want to share it with my colleague, I can do a screen capture of what I see within the view. I can save it as a JPEG, a PNG, GIF, or even a GeoTIFF that can be drawn up in the appropriate coordinate space in the GIS. And I can choose if I want to keep these headers and timestamps and scale bar on there as well. And I can download the image, and you can see how I'll name it with the the date that you're looking at in firms, and also the coordinates for the center of the view and the zoom scale that you're at. And I'll save that, and I can bring that up and display it here. Here is my screen capture that I just exported from firms. It includes that name that appears on the header. It also includes the scale bar and the timestamp that I specified I can toggle on or off. And I have a nice screen capture there I can share with somebody. The other thing you can do is if I build a map that I really like and I have all the layers that turned on as well that I would like and have it drawn at the scale I want, I can also share this link. I can copy this link. I can put it in a Teams chat to somebody and send it off. I can also click on the email button. It'll spawn a pre-populated email using whatever email service you use, and with that link in it, and you can send it off to a colleague. Or you can post it to social media. If you have a social media account set up, and just hit that button, and it'll have it all populated with the link. And so this is the conclusion of my demo here. So this is not intended to be an in-depth demo. It's just kind of a high level demo of how you can access all the various data layers in firms and get a general idea of the functionality. The only thing I want to highlight on the way out from this demo is Firms US Canada. If we jump into that map there, again, you have a very similar interface. Scale it up here to the advanced mode. And the difference is we have some additional layers that are not available in Firms Global. That being, we work with the National Interagency Fire Center to poll locations of current large wildland fire incidents that are ongoing in the United States. We also coordinate with Natural Resources Canada to poll information and data that they post on current large wildfires that are ongoing in Canada. On these various layers, you have the flexibility to threshold the sizes. So if I wanted to look at all the fires in the United States that are greater than 40 hectares versus those that are greater than 400 hectares, I can toggle that and filter it accordingly. And same thing with Canada. Nothing's being displayed there at the moment at the 404 hectare threshold. But if I drop it down to 40 hectares, there's one incident there in the Calgary area. We also include fire perimeters as well. We have some active incidents going on in the eastern part of the United States. So you can see here, these are perimeters that are actually provided by the incidents, and these are acquired and compiled, not using satellite imagery, but using typically airborne infrared resources and on-the-ground intelligence to delineate and update these perimeters on this every single day. And we provide them in the firms for context, so users can see what's going on with fire detections relative to those perimeters. And we also provide fire danger outlooks. This is the current fire danger outlook for today in the United States. Green being there's little or no risk, on up to brown being moderate risk. And we also have the forecasted fire danger product from NR Canada. And it'll draw in here in a second. They're not processing data for the entire Canadian area as of yet, but they will as the spring months wear on. So that is the conclusion of my demo there, and I'll jump back over to the slides one moment here. So the next part of our session today, we're going to hear from a colleague, Jenny Hewson, and she's going to be talking about the strengths and limitations of various satellites and sensors, and also the active fire detection data products that come from them. So with that, I'll turn it over to Jenny.
Well, thanks, Brad. Okay, so we've provided background on the theory of how active fire detection by satellites works and an introduction to NASA's FIRMS. We're now going to talk about multiple considerations or the relative strengths and limitations of different satellite-based active fire detection products. Due to the range of considerations or kind of the multiple nuances of different sensors and products, FIRMS makes available active fire detection data from multiple satellites. This is essentially because no one satellite meets all needs in terms of both the technical requirements and the fire management information needs. The technical requirements can include things such as whether global coverage is required. Not all active fire data is available globally. And if frequent observations are required, this will generally limit what's available to satellite sensors with a more coarse spatial resolution, such as MODIS, unless a constellation of fine spatial resolution sensors are used. Conversely, if relatively high spatial resolution data is required, these will generally be available less frequently due to the longer time between repeat satellite observations. And the accuracy, consistency, and reliability of different active fire detection data differs. This is why FIRMS includes multiple sources so that users can decide which data source best meets their needs for their area of interest. On the fire management side, these needs may also differ, and this drives which active fire data is the best fit or the most appropriate for the application. Perhaps the rapid detection of new ignitions is important, or the user needs to monitor fire progression. A fire manager may need to quickly assess the risk of a fire and the risk that it presents to nearby human populations or other resources such as infrastructure. Or a user may need to track smoke plumes from wildfires to assess the effects and then issue air quality information. These are all factors that can drive which data source or contextual information product is the most suitable for different user applications. So Brad mentioned both polar orbiting and geostationary satellites. FIRMS has historically relied on data products from polar orbiting satellites. But in the last 2 to 3 years, FIRMS has also incorporated data from geostationary satellites. So I'm going to review the major differences between these two, particularly with respect to active fire monitoring. The illustration on the top right is an example of a polar orbiting satellite. And as you can see, the satellite orbits from pole to pole while the Earth rotates. It keeps going over and over, covering more and more of the Earth on each overpass until over time the entire Earth is covered or imaged by the satellite sensor. Polar orbiters are considered sun synchronous. They move with the sun and they collect both daytime and nighttime sides of the Earth. They're located in a relatively low orbit, less than 1,000 kilometers above the Earth, and in general, they provide 1 to 2 observations at the same location daily. Although there are a number of additional considerations here, which we'll cover in the next slides. Additionally, at higher latitudes, there are more observations due to convergence towards the poles. The sensors cover what is called a swath, and different sensors have different defined swath widths. We'll also cover this a little later. Generally, polar orbiters also have higher spatial resolution. The animation on the lower right is of a geostationary satellite. And we can see that this satellite is locked on a particular location of the Earth. It stays stationary with respect to viewing the Earth. They're positioned as such for meteorological monitoring, as that's their primary application. They're located in higher orbits, approximately 35,000 kilometers. And because they are consistently viewing the same area of the Earth, i.e. they're observing a full disk of the Earth's hemisphere, they have multiple observations per hour, which can be very important for active fire monitoring. This is also a significant strength over polar orbiting satellites. Conversely, they have a relatively coarse spatial resolution. I mentioned swaths in the previous slide, and this looks quite busy at first, but it shows the relative ground swath for each of the sources of active fire data and imagery in FIRMS, plus a couple of additional sources of active fire data in light gray that are not included in FIRMS, but may be of interest. In addition to the swath, we've also included the spatial resolution of each of the active fire products, plus the temporal resolution. The geostationary satellites are listed at the top, then the polar orbiting satellites. First, we have GOES 16 and 18, also called GOES East and West, and these carry the Advanced Baseline Imager, or ABI sensor. These are centered primarily over the Americas at -75.2 and -137.2 degrees longitude. The swath is over 10,000 kilometers. And as we saw in the previous slide, they image a full disk of Earth. The temporal resolution of these satellites is approximately every 10 minutes, which can be incredibly useful, but they also have a much coarser spatial resolution in terms of the active fire product of approximately 2,000 meters or 2 kilometers. Meteosat 9 and 11 carry the Spinning Enhanced Visible and Infrared Imager, or SEVIRI, instrument. They're centered over Europe and Africa at 0 degrees and 45.5 degrees longitude. The swath is approximately 11,400 kilometers, and the spatial resolution of the active fire products is 3,000 meters. Again, the high temporal resolution makes them very useful for active fire detection. They image a full disk of Earth every 15 minutes or less. Himawari 9 carries the Advanced Himawari Imager, or AHI. It's centered over Asia at approximately 140 degrees longitude, and the spatial resolution of the active fire products is 2,000 meters. It's the same as GOES 16 and 18. The temporal resolution is also very high. It images the full disk of Earth every 10 minutes, and the swath width is approximately 11,000 kilometers. So the combined spatial coverage provided by these three sets of geostationary satellites means almost consistent monitoring of the Earth, which can be very helpful in active fire detection. The remaining satellites here are polar orbiting satellites, and what we notice initially is that the polar orbiters have a much narrower swath width. First are SMPP, a joint NASA-NOAA mission, and NOAA 20 and 21. These have a swath width of 3,000 kilometers. They each orbit the Earth twice daily, and they each carry the VIIRS instrument. The spatial resolution, as you can see, of the active fire detections is 375 meters. Next up, Terra and Aqua both carry the MODIS instrument. The swath of MODIS is 2,330 kilometers. They also orbit the Earth twice daily, and the detections are 1 kilometer or 1,000 meters. MODIS is actually considered the workhorse of active fire detection, with archives spanning over 20 years. As I mentioned, we've also listed Sentinel-3A and B, as well as Sentinel-2A, B, and C. The fire detections are available from these sensors, but they're not currently available through firms, though they may be of interest for you to explore. And finally, Landsat 8 and 9, which carry the Operational Land Imager, or OLI. As you can see, they have the narrowest swath width of just 185 kilometers. This in turn drives the temporal frequency, which is approximately 8 days, considering both Landsat 8 and 9 combined. But the fire detection from OLI has a really high spatial resolution of approximately 30 meters. As Brad mentioned, fire detections from Landsat 8 and 9 are available in firms for the continental US as well as parts of Canada. So I mentioned this spatial coverage provided by these three sets of geostationary satellites. And as you can see, the coverage of each satellite is approximately 120 degrees longitude, and there's a lot of overlap in the coverage. So moving left to right, we have GOES 18 and 16, Meteosat 11 and 9, and Himawari 9 on the right-hand side. One note is that Meteosat 9, or IODC, is now centered at 45.5 degrees longitude. And this is a comparison of the coverage from geostationary and polar orbiting satellites at two different timestamps. The geostationary satellites are on the top, and this is what they are seeing at 6:14 UTC on the 27th of March. Himawari is on the far right. It's centered at 140 degrees longitude. Meteosat 9 is on the left of Himawari, and then GOES 18 is all the way over on the left. And these are all viewing areas of the Earth where it's daytime. It's late afternoon in Sydney, Australia, for example. Then in the lower left is a similar timestamp, 6:16 UTC on the 27th of March. And this is MODIS aboard Terra as Terra orbits the Earth. As you can see, much of the world is black, as Terra has not imaged much of the world as yet at this time on the 27th of March. On the right, we're looking at 6 hours later, 12:17 UTC, and now you can see it's nighttime in much of the area that Himawari is continually viewing, and now daytime in much of the area covered by Meteosat 9 and Meteosat 11. Again, these satellites are centered at 45.5 and 0 degrees longitude. And then in the lower right, we can see that more of the Earth has now been imaged by MODIS as Terra continues its daily orbit around the Earth. Okay, so we've talked about considerations in spatial coverage of the satellites, in the temporal frequency, in the spatial resolution. And now we're going to spend a minute on the sensor characteristics and the spatial coverage of satellites and how that impacts pixel size. This is something to consider when using data and imagery, particularly from Terra and Aqua and the geostationary satellites. As I mentioned, Terra and Aqua continually image swaths of 2,330 kilometers wide as they orbit the Earth, and the pixels actually become elongated on the outer or east-west edges of the swath. In this illustration on the left, the nadir pixel size are directly below the satellite in the middle of the swath. The pixel size is 1 kilometer, but it actually grows in the across-track direction to almost 5 kilometers, as you can see on the swath edge, as the viewing angle increases away from nadir. This results in these elongated pixels, and it's important because any fire that is detected could be anywhere within this elongated pixel. This change in pixel size is less of a consideration in VIAs due to the sensor design and constrained pixel growth. And with Landsat, it isn't a consideration because Landsat doesn't have an expansive field of view. Again, the swath width of Landsat is much smaller. It's 185 kilometers. For geostationary satellites, we've seen that the area continually imaged by these satellites is huge. It's around 11,000 kilometers east to west and north to south. Now, if you think of a flashlight beam focused on an area, the area in the middle of the beam is very bright or resolute, whereas areas further away from the middle become less bright and more blurry. Geostationary satellite imaging is very similar. Areas of the Earth directly below the satellite or sub-satellite are the most resolute, and for GOES 16 and 18, they have a spatial resolution of 2 kilometers, as you can see in this illustration on the right. But as the sensor's field of view expands away from that sub-satellite point, and the sensor views off nadir, the size of the pixel changes systematically, as you can see in this illustration. At 70 degrees, for example, the pixel has now grown to 14.4 kilometers squared. And as with MODIS, this has implications for active fire detection. Again, any fire that's detected could be anywhere within this increasingly elongated and rhomboid-shaped pixel. This illustrates this change in pixel size for GOES 18, 16, Meteosat, and Himawari as this off-nadir view increases. At approximately 50 degrees, for example, the pixel area is almost 8 kilometers squared. Okay, so there are multiple considerations, as we mentioned, when using satellite-based active fire detections or imagery. Here they're listed as strengths and limitations, but the key is really to think about what is the most suitable or useful for a particular application of a particular area at a particular time period, bearing in mind that no one sensor meets all requirements. On the left are the relative strengths and limitations of polar orbiting satellites, and geostationary satellites are on the right. So polar orbiters, as I've mentioned, they have a long history of use for active fire detection. The algorithm development is therefore much more mature. I mentioned MODIS on board Terra and Aqua, and again, this is the workhorse for active fire detection, dating back to the early 2000s. Users are also generally more familiar with these data. Polar orbiters have a higher spatial resolution, MODIS active fire detections have a spatial resolution of 1 kilometer, VIAs 375 meters, Landsat 30 meters, and then the Sentinel 20 meters. They also observe twice a day, and more so towards the poles. They have a higher spectral resolution, and the sensors are typically optimized to map or monitor environmental phenomena such as fires. The data from these satellites are delivered to firms and made available to users relatively quickly. We will delve into latency more in the next webinar, but generally detection data from MODIS and VIAs is delivered to firms within 3 hours of observation. The near real-time detection data from Landsat is delivered within 30 minutes of observation. Again, Landsat detection data is available for the continental US, as well as parts of southern Canada and northern Mexico. FIRMS also has what's termed ultra real-time detection data, or URT data, from MODIS and VIAs. These are generated by the Space Science and Engineering Center in Wisconsin, and these data are available in firms within 5 minutes of satellite observation. Again, these are available for the continental US, southern Canada, and Mexico. And I've noted on this slide that it's generally within 2 minutes of satellite observation. As I have mentioned previously, the geostationary satellites cover an entire hemisphere or a disk of Earth, and this can be very useful because of the frequent monitoring. Because they're observing the same area of Earth consistently, these observations are conducted multiple times hourly, approximately every 10 to 15 minutes for a full disk. The active fire detections from the geostationary satellites are generally delivered to firms within 20 to 30 minutes after satellite observation. Because of this really high temporal resolution, geostationary satellites provide frequent sampling of fire activity, which can enable earlier detection of new ignitions, and it can be particularly useful for tracking fast-moving fires or short-lived or transient fires. And again, because of the temporal resolution, geostationary active fire data can be helpful for kind of filling in or gap filling between the polar orbiting detections. Also, because of their expansive field of view, fewer satellites are needed for complete global coverage. So these are all the relative strengths of the polar orbiting satellites and the geostationary satellites. We've also listed a number of limitations, but again, this depends on the application, the context, etc. So for polar orbiters, as we've seen, they don't provide continuous coverage of the Earth at one time unless a constellation is used, and the frequency of observations really varies among the instruments. VIAs and MODIS have daily global coverage, whereas Landsat 8 and 9 each image the entire Earth approximately every 16 days, at least at lower latitudes, or 8 to 9 days with the two satellites combined. For the 3 Sentinel satellites, A, B, and C, it's approximately 3 to 4 days. Another consideration is that multiple images acquired at the same location on the same day may not have the same view geometry. And as we saw in the previous slide, MODIS on board Terra and Aqua experiences this systematic pixel growth away from nadir, resulting in these elongated pixels. Also, MODIS is nearing end of life due to the end of life of Terra and Aqua. These again have been the workhorse for over the last 20 years for active fire detection. And then there are multiple environmental conditions such as cloud, smoke, etc., that can obscure observation and prevent the detection of fires. Because Terra and Aqua only observe twice a day, if there are clouds present during both or even one of these overpasses, fires could be missed. As far as the limitations of geostationary satellites, these satellites are primarily designed for meteorological monitoring and weather applications. So as such, there are inherent platform and sensor characteristics that really need to be considered when used for active fire detection. As we saw in the previous slide, this distortion occurs with distance from nadir. The use of geostationary satellites for active fire detection is also relatively new, which means there is ongoing algorithm refinement and development. As I've mentioned, they have a more coarse spatial resolution, and the spectral resolution is not optimized for active fire detection. Additionally, the data accuracy can be inconsistent with a higher number of false positives. And in firms, there is a harmonized global geostationary active fire product that has been filtered to reduce detections. Okay, so now we will move on to a few demos that will highlight considerations for using active fire detections and imagery. So now I've switched over to firms, the actual platform, to highlight a few considerations when using satellite-based active fire detections and imagery. Brad has provided an overview of the firm's maps. And again, there are two versions. There's the Fire Map Global and the Fire Map USA and Canada. And these both fall within the firm's US, Canada, and firm's global platforms. We're going to use both of those here to explore different sensors, different products, so that you can take kind of the nuances of these different products into consideration when assessing what to use for a particular location, a particular application, etc. Okay, in this first example, we're going to use firms US Canada, as you can see here, and imagery from polar orbiting satellites to illustrate, firstly, how the spatial coverage of footprint and the temporal frequency really varies among the different polar orbiters, and secondly, how this impacts the availability and the utility of different active fire products. We're going to focus on a fire that occurred in Northeast Oregon in September 2022. It was called the Double Creek Fire, and it was located east of Flora, Oregon. Okay, I have switched, Brad showed you the different modes, and I have switched from the basic mode, which is the default entry mode, to the advanced mode. And I have located Flora here using the location tool up here and popped in Flora, Oregon under Find Location. I've also set the date up here for the 10th of September 2022. And finally, I have toggled on the Modus Terra True Color Composite Imagery. Okay, if I now just scroll out slightly, you will begin to be able to see, if I also scroll down, the broad swaths of MODIS imagery. You can see the swaths here, 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 and they extend all the way up as Terra continues to orbit over the Earth from pole to pole. These swaths are 2,330 kilometers wide, and all of these together make up the daily global coverage of MODIS. Now, we do see these small gaps between the swaths, and if I now pop on the Allow Multi-Layer selection here, and I add the VIIRS NOAA 20 True Color Composite imagery here, I'm now going to take this opacity tool down here, and if I change the opacity, you can see, if you watch between these swaths, you can see that Viers actually has complete coverage and even some overlap between the different swaths. And that's because the Viers instrument, which again is on board NOAA 20, NOAA 21, and SMPP, has a wider swath of 3,000 kilometers. The other thing that I wanted to quickly point out is that generally there's more cloud coverage in the afternoon versus the morning. As we've mentioned, MODIS on board Terra is a morning overpass, and the Viers instruments are all afternoon overpasses. And generally there's more clouds present in the afternoon. If you watch these areas here around Texas and Mexico, you can see that in the afternoon there are more clouds present. Now, it was generally quite a cloudy day overall in this in the Americas around here, but definitely more cloud in the afternoon. Okay, I'm going to now turn off the Viers NOAA 20 and let me pop back on the MODIS imagery. And I also wanted to note, you see these massive smoke plumes up in here that are coming from the wildfires that were occurring in this area and then emanating out into the Pacific Ocean. Now I'm going to add the another data layer. This is the Landsat 8.9 true color imagery for the 10th of September. And let me just bring it up here. Okay, now you can just about see the swaths of the Earth that were observed by Landsat on the 10th of September. But I want to highlight this handy layer down here. This is the dark gray layer, and it provides kind of a neutral background. So it's useful in examples where we really need some contrast. So I wanted to use this to highlight, again, the Landsat imagery has a very narrow swath width. It's 185 kilometers. And if we now pop back on the MODIS True Color Composite, and then we use the opacity tool, you can clearly see the area covered by one MODIS swath compared to the width of the swath of the Landsat imagery. Okay, this is why the repeat frequency of Landsat is each Landsat instrument, Landsat 8 and Landsat 9, has a repeat frequency of approximately 16 days. But with the combined Landsat 8 and 9, it pulls it down to between 8 and 9 days combined. But it obviously takes a lot longer for Landsat to rotate around the Earth and complete global coverage of the Earth. Conversely, while the temporal frequency of Landsat is much lower, it has a much higher spatial resolution. In fact, the spatial resolution of the true color composite imagery of Landsat is 30 meters compared to 250 meters for the Viers imagery and the MODIS imagery. Okay, if you note on the 10th of September, the Landsat actually passed over very close to Flora, Oregon. And now we are going to zoom in to this location. Okay, and you may actually be able to see, this is actually the fire, the Double Creek fire right here. I can now turn off Flora. I'm going to now pop on the false color composite imagery. This will actually be discussed in the next webinar, but I'm just using it here to to really provide some delineation on the area that had burned by the 10th of September. You can actually also turn off the dark grey layer as well. Okay, and so again, this just helps you see kind of the delineation of the area that's burned. Now I'm going to add the MODIS active fire data, which will be right up here in the polar orbiting hotspots and active fires. And you can see we're looking at all of the fire detections for the 10th of September 2022 that were detected by MODIS. If I now bring up the attributes for one active fire, you can see again it contains the latitude, longitude, the brightness, the scan and track, the time it was acquired. This defaults to my local time, which is Mountain Daylight Time in the US, and we can toggle over to UTC as well. So this was acquired at approximately 5 in the morning UTC. The satellite was Terra, the MODIS instrument. This is a confidence factor here. And then some additional information. This was a nighttime overpass, considered a nighttime overpass. And we also have the brightness temperature and the FRP as well. All right, I'm now going to change the color of the Landsat active fire data that were collected using the OLI instrument. Let me change this to yellow and pop this on. Okay, so we're now looking at all of the Landsat fire detections from that one Landsat overpass on the 10th of September in yellow and the MODIS detections in red. And you very quickly notice that there are many more Landsat active fire detections than there are MODIS detections. This really shows the utility of the Landsat active fire data when they're available. These data, again, all these little yellow squares, these data are able to provide much more kind of contextual information. They're able to provide information on kind of active fire fronts. They're much more spatially explicit. They're able to detect smaller flaming fires as small as a few square meters or smaller. And they can also detect smaller scattered fires within the fire perimeter, as you can see here. Additionally, due to the morning overpass of Landsat, in addition to Terra, Landsat also has a morning overpass. These can be useful in situations where, for example, nighttime aerial flights have been flown, and this information can be used to kind of supplement that first thing in the morning. The data are also available within firms within 30 minutes of overpass. But note again that the Landsat has this much lower temporal frequency. It's only available every 8 to 9 days. And also currently the Landsat active fire are only available in firms for the continental US, as well as parts of southern Canada and northern Mexico. All right, so the key takeaways from this demo are really the impact of spatial resolution and how that can drive kind of what the active fire detections are available in terms of what the sensor can pick up, the temporal frequency and the impact that has on when fires are detected, and then also the spatial coverage, which I showed with the different swath widths of the MODIS versus Landsat. All right, moving on to a second demo. In this example, we're going to illustrate the pixel distortion that occurs in MODIS at extreme view angles. If you remember in the slides, we looked at how as the sensor views off nadir, the view angle increases, resulting in these elongated pixels at the edge of the swath. So for fire applications, this is a very real consideration, because again, a fire that is detected within that elongated pixel, which could be up to almost 5 kilometers, a fire that's detected within that can be anywhere in that pixel. All right, as you will see, I've now moved into Firms Global. And again, I'm in the advanced mode. I have used the location tool here to locate an area called Toshka Lakes in the New Valley near Lake Nasser in Egypt. And I've also set the date to, incorrectly, I wanted to set the date to the 17th of March. All right, I am also going to now toggle on the Modus Terra True Color Composite. And what you can see is very clearly the outline of the lake here. There's also cultivation going on around here. And if we zoom in again, you can really see a pretty clear perimeter boundary of the lake. Again, the imagery is 250 meters, but you can see this. You can see some the individual pixels and a lot of clear contrast. All right, if I now pop on the orbit tracks for Modus Terra and zoom out, what you can see here, this is the Terra Modus track for the 17th of March, and this image was acquired approximately 7:41 UTC. And what we can see is the Toshka Lakes were right below the satellite when it overpassed on the 25th of March. It was right in the middle of the swath. So there is minimal pixel distortion that occurred on that date due to where the lake was located within that swath. Again, you can see it is nicely right in the middle of the swath here. All right, let me now zoom back in and just take this off for a moment. If we now change the date, we can change the date down here. We can also change the date up here to the 28th of March. And what you can see are now that the Toshka Lake is right at the edge of this swath. If I just zoom out. And pop back on the Terra. Okay, you can see now the middle of the swath is all the way over here, and Toshka Lake is all the way over to the edge of the swath here. And so what you now see is significant distortion in the image. And again, this is because these elongated pixels are occurring as a result of the extreme view angle. If I just pop this back to the 17th of March again, then you can see this was in the middle of the swath, and the pixel resolution is much more defined. So the key takeaways from this demo are the effects of view angle on pixel distortion, which is a consideration when using the data, the active fire data from Aqua and Terra in terms of the MODIS instrument, and then also the geostationary instrument. As I mentioned in the slides, it's less of a factor for vias due to sensor design and constrained pixel growth, and it really isn't a factor for Landsat, largely due to it has a much more narrow swath width. All right, and then in this final example, we're going to actually look at a recent fire that occurred southeast of Andong in South Korea. And we're going to illustrate a couple of considerations. Firstly, the benefits of the temporal resolution of the geostationary satellites. And also we're going to look at the impact of systematic growth in pixel size. Again, I'm in the firm's global instance, and I am again in the advanced mode. And then this example, we're actually going to use Himawari. So Himawari is a Japanese meteorological geostationary satellite. We've discussed it in the slides as well. It's centered over the equator at 140 degrees longitude. And data from Himawari is particularly useful for Japan, East Asia, and the Western Pacific region. I have located Andong here, and I actually used the lat long of the area, which is another option available in the location tool. And then I have selected under overlays. Again, there are these handy additional layers, and I've selected the detailed layer to label the different locations here. Finally, I've set the calendar to the 25th of March 2025. As you may be aware, there are a number of wildfires that occurred in South Korea recently. And now I'm actually going to toggle on the Himawari active fire detections here. And as you can see, there were a lot of detections of this wildfire southeast of Andong on the 25th of March. Okay, I quickly want to move to right in the middle of the Pacific Ocean. And the reason being that the Himawari satellite, which again uses the advanced Himawari imager to collect the data that are then used to generate the active fire data from Himawari. And so this is the point subnadir. And as you can see, the fires in South Korea. South Korea is located further north of the central viewing point of Himawari. And in fact, Andong is located at nearly 37 degrees north and 128 degrees longitude. And so if you remember, as we move away from this nadir view, the pixels begin to change in size. The systematic pixel size increase that occurs in the geostationary satellites. So again, let me scroll back to the area we're interested in, this fire southeast of Andong. And what you actually are now starting to see is the impact of the systematic increase in pixel size. The pixel size display is set to 2 kilometers by 2 kilometers, but we are starting to see the gaps between the adjacent pixels due to this increase in pixel size. Again, as we discussed earlier, the use of geostationary satellites for active fire monitoring is relatively new, so there can be a a higher rate of false detections. So these nuances need to be taken into consideration. However, if we now explore the active fire data from the polar orbiting satellites, we're going to see the utility of all of these Himawari detections. All right. I'm just going to select the time-based option here, and I'm going to set the time to 1 day. Click on the sub-daily. We will delve into this sub-daily module in part 2, but I'm just going to quickly use it here to highlight this one point that I want to make. So this is now, we are looking at 11 a.m. UTC on the 25th of March. And we're looking at a 10-hour reach back. As you can see in the timeline at the bottom, we're now looking at a 10-hour period here. So we're looking at all of the detections by Himawari between 1 a.m. and 11 a.m. And as you can see, these are displayed in kind of increments of less than 1 hour, which are all of these dark red spots, 1 to 3 hours, which are the bright red pixels, and then 3 to 6 hours, which are the orange pixels. And so there are a number of different detections during this 10-hour period. If we now toggle on the polar orbiting satellite, and I'm going to put all of them on except for the Landsat active fire detections, because again they are currently available for the continental US, southern Canada and northern Mexico. We can see that the active fire detections from the polar orbiters are only available over this area, whereas we also identified all of these active detections from Himawari. The reason that I wanted to highlight this is that during this 10-hour period, because Himawari is continually looking at this area and completing an entire disk in terms of coverage every 10 to 15 minutes, it is able to pick up all of the active fire activity between this 10-hour period. Whereas for the polar orbiters, they only overpassed this area one time during that 10-hour period. And in fact, if we zoom into the modus terra, let me just take these up. As you can see, there was only this one overpass that occurred at 01:24 a.m. on the 25th of March. Again, there will be another overpass later on, but between this overpass and the next overpass, all of these detections were identified by Himawari. Okay, so the key considerations or the key takeaways from this example are, again, the systematic increase in pixel size that occurs with the geostationary satellites needs to be taken into consideration with active fire detections, because again, as the pixel size grows, a fire that is detected within that pixel can be anywhere within that pixel as it grows and grows. The use of geostationary satellites for active fire detection is relatively new, and the algorithms are still being refined. So there could be additional false detections. However, the temporal resolution, as we've seen from this fire southeast of Andong, the temporal resolution of the geostationary satellites, such as Himawari, can be really useful for in between the polar orbiting overpasses. Conversely, MODIS and VIAs have this long history of use in terms of active fire detection. They have a much higher spatial resolution. As you can see, if I pop on, as you can see here, these in fact are the VIAs, 375 meter pixels, and the MODIS 1 kilometer pixels. So with the VIAs, we're getting even more contextual information. And finally, the MODIS and VIAs are optimized for environmental monitoring, such as fire. So all of these nuances should be taken into consideration when using the different active fire products. And that is why within firms, we include so many different sources of active fire data as well as imagery. Thank you.
Thanks, Jenny. Let's take a quick minute to review some of the key points from part 1 of our training. First, Brad introduced NASA Firms. Firms provides access to near real-time data related to wildfire activity, as well as interfaces and services to help with fire management and response, as well as scientific research. Firms contains 2 distinct applications, Firms Global and Firms US-Canada. These 2 applications are very similar and contain the same data sources, but Firms US-Canada focuses on the US and Canada geographic area and contains some additional data sets relevant for fire management agencies in the US and Canada. Firms provides many options for imagery and data products for detecting, monitoring, and assessing the effects of fires. Active fire detection products are the most frequently used and are available from several different sensors. We learned that fires emit strongly in the mid-wave IR and long-wave IR, and sensors use this to detect active fires. Additional wavelengths are used to reject false positives, filter out clouds, sun glint, and coastal regions. Each active fire detection represents the center of a pixel that has been flagged as containing 1 or more fires. And the size of the pixel varies depending on the spatial resolution of the sensor, from about 30 meters to about 3 kilometers. Firms provides global active fire data and imagery from 16 sensors that are made available via partnerships with universities as well as other space agencies. Firms also includes all of these sensors because no one sensor meets all of the requirements needed for fire management. The key is to choose the product that fits your question or application for your particular area and time period. Polar orbiting sensors have higher spatial resolution, which allows them to detect more and smaller fires, even as small as 1 meter squared for Landsat. But fire detections from polar sensors are only available twice a day or less frequently if the sensor has a smaller swath width. Geostationary sensors cover an entire hemisphere and make observations multiple times per hour, but their spatial resolution is lower, and these algorithms are less mature and can have many false positives. These observations might be helpful for tracking fast-moving fires or providing information between polar observations. Brad provided a live demonstration of Firms showing how to navigate the fire map, find active fire detections, view additional satellite imagery, and use the location, mapping, and sharing capabilities. Jenny showed the impacts of swath width and spatial resolution on fire detections for a fire in Oregon, and then showed the impacts of higher view angles that occur as you move away from nadir on pixel distortion. In our next part, in part 2, we'll show how Firms can be used for fire monitoring and evaluation, and we'll discuss factors that can impact a sensor's ability to detect a wildfire. Quick reminder, this training series will have 1 homework assignment, You can access the homework from the training webpage starting April 31st, and answers should be submitted via Google Forms by May 14th. Certificates of completion will be issued to participants who attend all of the lab trainings and submit the homework before that deadline. Certificates will be issued by email about 2 months after the training. Here, we've included the contact information for myself and today's speakers, as well as links to the ARSET website, YouTube channel, and Twitter or X, and our sister program, Develop. And we've also included the publications that were referenced throughout today's training. And finally, some additional links and resources, and this can be found on the training webpage. Thank you so much for joining us today. We will now transition over to the Q&A. And before we start today's Q&A session, just another big thank you to our guest instructors, Jenny and Brad. And while Jenny can't join us for this part of the Q&A, we are joined by Diane Davies, who is the Lance Operations Manager. So thank you, Diane, for joining us for the Q&A. I realize we've gone a little bit long today, so we probably won't be able to answer all of the questions that you all have entered, but we'll try to address questions for the next maybe 10 minutes or so, depending on Brad and Diane, if you can hang around, and be sure that all of the questions that you've entered we'll address offline and then post the Q&A doc to the training page after today. So with that, Brad and Diane, is it okay if we take a few questions for about 10 minutes or so at least?
Sure.
Sure thing.
Awesome, thank you. So question 1, do the points reported by firms represent the spatial centroid of an area with anomalous reflectance detected by the sensor, or do they correspond to the center of the sensor pixel that recorded the thermal anomaly? How is the location reported by firms interpreted exactly, and what's the underlying physical principle behind the sensor's detection of these anomalies? That's a big question, so I'll turn it over to either Brad or Diane. Which one of you wants to address this one?
I can take a stab at it, and Brad can chime in if he likes. So the point corresponds to the center of the pixel that was flagged as having a thermal anomaly. So I don't know if we can click on that link from the FAQ, but I think that it helps explain, it helps give a good idea of what you can see. Doesn't show very well. Okay, but basically you have a pixel and we give you the center of that pixel size. And there could be one or more fires within that pixel. That's it. It's that question. What does the fire detection mean on the ground? 1, 2, 3, fourth one down. That's essentially what it is. And so for MODIS, you have a pixel that's approximately 1 kilometer, but this does vary according to the scan and track. It's not exactly 1 kilometer, it's an approximate one. Those are the approximate dimension. So I hope that this sort of helps answer the question. So you can have, one fire in that particular pixel, or you might have more than one fire. And you can't tell exactly where that fire is. You just know that it's somewhere within that pixel.
That was a great response, Diane. I would only add that, yeah, if you have a very large area of fire, you could have multiple fire detections there, and so you would have a potential grouping or cluster of fire detections that were occurring with that fire activity area. So as what Diane just described there, in that case, you would have the centroid for each one of those pixels that where fire activity was detected.
Okay, and I think a follow-up is, and I see a written answer, is the physical principle behind the sensor's detection. So Brad, you alluded to this briefly during the slides, but then I think we'll have some supplemental material on the training page for this. But do you want to speak to this part?
Yes, the fire detection algorithm that's used for MODIS and VIIRS are very similar, but these algorithms, these current day algorithms that are being applied with these sensors are based on what we call legacy or heritage fire detection algorithms that, reach back, clear back into the early 80s with the AVHR and other meteorological sensors where, that had thermal detection or had thermal bands on them and were used for meteorological purposes, but it was determined they have the right bands to be used for fire detection, at the 4 and 11 micron wavelengths, or what we call the mid-wave and infrared and the long-wave infrared. And so those that response curve that was shown earlier in the presentations, showing how you got that strong response from fires in the 4 micron or the mid-wave infrared. That's the key thing, or key response that's leveraged in fire detection. And that difference in the response between the long-wave and the mid-wave infrared is helpful too in helping, verify and ensure that the accuracy of the fire detections, as well as to when you go into what's called the contextual mode, you're looking at those potential fire pixels that have been identified and looking at that particular pixel in the neighborhood of the pixels that are around it. So that center pixel that's being evaluated is kind of taken out of consideration. We're saying we're looking at the neighbors and say, well, let's look at our neighbors here that are not potential fire pixels and try to get an idea of what that pixel we're analyzing looks like if it wasn't on fire. And so it uses a statistical approach to look at the response in those critical bands to make that determination and analyze it and say, yes, we do have a significant difference here, that this does look like a fire, and we can flag that fire as the detection with a certain degree of confidence. And we highlighted the confidence ratings that are available with the detection data also. So looking forward in the future, as you can imagine, there's a lot of attention and interest in refining, this current generation of active fire detection algorithms, using more things like AI and machine learning and whatnot to train these detection algorithms and classifiers to identify fire as well. And so a lot of that work is ongoing with all these various polar orbiting and geostationary sensors.
Thank you. Okay, question 2. I'm from Nepal and have been using FIRM since 2013. Last year we suppressed one fire in Kathmandu, which took us around 12 hours. I understand that in Nepal, Aqua and Terra run around 10:30 and 2:45 p.m. overpass times. The fire we suppressed was big, and took around, lasted from about 6 a.m. to 6 p.m. When checking the active fire record of FIRMs that day and the next day, it never showed on the record. And what could be the reason?
So I'm guessing that the reason for that is likely to have been cloud cover or heavy smoke, but really without knowing the date, or it could be that there was an issue with the instrument at that time. That's another possibility. But if you want to get in touch and let us know more specifically what date it was and what the location is, then we'd be very happy to look into it.
And I think we'll go into some techniques you can use to identify reasons why there might not be a fire of interest included in FIRMs in our session next week.
That's very true. So yes, hopefully next week you'll know all the answers. Good point.
Question 3. Doesn't Landsat 8 and 9 thermal infrared sensor use thermal bands in the range 10 to 12 micrometers, which essentially belongs to the 8 to 14 micrometer region? We've been taught in one of our courses that this band is ideal for measuring radiant temperatures of objects that occur naturally on the Earth's surface. For very hot objects, such as wildfires or volcanoes, we use thermal bands sensitive to the 3 to 5 micrometer region. How reliable is Landsat for wildfire detection? Because wildfires usually burn at 800 plus degrees Celsius.
Yeah, Brad here. I'll take that one. Very good question and statements there. Those are true statements. What I will emphasize in this response is for the Landsat active fire detection product, TIRS is not used. The operational land imager or OLI sensor is used, in which it does not have any thermal bands on the OLI sensor. So the shortwave infrared bands are key to the fire detection on with the Landsat active fire detection algorithm, particularly the 2.1 micron band. And the visible and near infrared bands are also used to support identifying other features, the masking process and whatnot, and helping to reject false positives. So Landsat active fire detection data is totally based off of the OLI sensor. And again, using that strong response in that shortwave infrared band to the energy emitted by fire.
Excellent. Okay, question 4. What is the need of combining 15 different satellite missions data? Is it for improving the temporal resolution or any other purpose?
Yeah, I'll take this one. Yes, it's primarily for improving the temporal resolution. So initially, when we started, we only had data from MODIS, Aqua, and Terra, so that gave us approximately 2 overpasses per day per satellite. And obviously, we added in VIIRS, but yeah, it just gives us more looks, which ultimately is helpful for users on the ground, and can certainly with the geostationary and more looks, you get to a better understanding of the progression of a fire.
Okay, thanks. Question 5, is it possible to see the footprint of the satellite on the map in order to know which area was sensed, especially for Landsat, which has a small footprint or swath?
So yeah, that's a great question, and unfortunately, it's not something that we currently have in firms. I put a link in the Q&A there, which will enable you to look at the orbit track, so that will give you an idea of where the satellite is heading and what time, and that it'll give you an indication. But it is something that we plan to add to firms, hopefully in the relatively near future.
Great. And maybe this will be our last question for time. Can firms also help in forecasting fires?
Yeah, Brad here, I'll take that one. Yes, in firms US Canada, that particular application, a couple of products are provided. These products are not provided by NASA. They're provided by Natural Resources Canada, specifically the Canada Wildfire Information System. They provide a daily fire danger forecast year-round for the all of Canada. So that those data are provided by the Canadian folks, and they're integrated into firms US Canada as a layer. And similarly for the United States, the National Predictive Services Program, which is located at what we call the NIC, or the National Interagency Coordination Center, which is in Boise, Idaho, they issue a somewhat different fire danger forecast. It's called the Significant Fire Potential product, and that's available for the continental United States and Alaska. And we integrate that into firms US Canada also.
Excellent. Okay, so I think we'll probably close since we're well over time today. So I just want to extend another big thank you to our guest instructors for an amazingly informative training part today. And just a reminder to everybody, the requirements for getting a certificate are to attend all of our live trainings, all 3 parts for this training series, as well as complete the homework assignment. And the homework assignment will be available on the training page the day after our last session, so May 1st. And I apologize for the typo that I put in the slides. That's at April 31st. Many apologies there. So we hope you'll join us next week for part 2, and I hope everyone has a great rest of their day.